I want to thank the organizers for putting on a very nice conference and for giving me the opportunity to tell you guys about what we've been working on the JILA KRB experiment in Jungi's group. In particular, I'm going to tell you about Tunable XXZ spin dynamics with polar molecules, which is a lot of words, but we'll get into that. So generically, we're really interested in studying the extended Fermi-Hubbard model, where we have some sort of long-range interactions. In our case, it's going to be dipole-dipole, tunneling between sites on, for example, an optical lattice, and then on-site interactions. Since the Fermi-Hubbard extended Fermi-Hubbard model, or kind of subsets of it, can explain a lot of, or may explain a lot of really interesting dynamics like high temperature superconductivity in cuprates or various phenomena in quantum magnetism like spin liquids. And if you take the tunneling to zero, you're left with an XXZ spin model which contains an Ising term and a spin exchange term. And I'll spend most of my talk talking about that subset of the extended Fermi-Hubbard model. We also can rewrite it where we have a term with coefficient J perp, which is defining an isotropic interaction between spins, and a coefficient chi, which is Jz minus J perp in this other version of the model, which describes the anisotropy of the interaction. And I'll be switching between these two notations kind of as is convenient for the particular topic that I'm discussing. And this XXZ model generalizes a lot of the kind of classic spin models that people think about in many-body physics, like the Ising model, the isotropic Heisenberg model, or the XY model. So why do we want to use molecules to study these sorts of extended Fermi-Hubbard models? Well, they have, as a lot of people have talked about, electric dipole interactions, which are strong, much stronger than magnetic interactions between atoms. They're long-ranged, which allows kind of implementation of like other sorts of rich many-body dynamics. They're anisotropic, which allows tunability, and they're continuously tunable with application of electric fields. I'll talk about that in some more detail. In addition, we can have long coherence between molecular states in an appropriate environment. And then I think most excitingly, like the molecules are real quantum objects that have bosonic or fermionic statistics and can move around in a coherent way. So overall, there are a lot of exciting prospects for realizing some of these in molecules. So I'm going to tell you about some work from the last 10 or so years on the JILA KRB experiments towards realizing different subsets of this model. In 2013, with molecules in a 3D lattice, we're able to explore the spin exchange We're able to explore the spin exchange dynamics. Then, more recently, we've been able to More recently, we've been able to apply electric fields to the molecules and tune the interactions within the XXZ Hamiltonian. I'll also tell you about another picture of the XXZ Hamiltonian that we can implement with itinerant molecules rather than molecules pinned in a lattice. And then finally, I'll tell you about some very recent work where we've turned on tunneling of the molecules within the lattice, and we see some pretty exciting dynamics in that regime. So, how do we actually implement the XXZ model with molecules? We'll take the ground rotational state and the first excited rotational state as our spin 1/2 system. And then we can apply an electric field which polarizes the molecules in the lab frame, which introduces Ising type interactions. There are also spin exchange interactions where a rotational excitation can transfer from one molecule to another, and the strength of those interactions decreases with increasing electric fields as more and more rotational states get mixed in. Also, we have a variety of single particle energy shifts of the molecules. And controlling these is a big part of actually realizing these models in molecules. So in particular, we can talk about molecules in a deep three-dimensional lattice where they're pinned in place. In the experiments that I'm talking about, there's a pretty low filling fraction of something like 10%. So the particular disorder in each molecule's environment determines a lot of its dynamics. Also, since we have dipolar molecules, there's a particular form for the interaction that has a 1 over r cubed distance dependence in the usual dipolar anisotropy. Since it's molecules in a lattice, there are also certain dominant single particle effects. I'll talk more about how we control those. And then here we're using a lattice with 532 nanometers spacing between sites. So that fixes a strength of the interactions that at zero field reaches a couple hundred hertz with the KRB molecules, which have about half a Debye dipole moment. So in 2013, we're able to only apply low electric fields and explore this regime. More recently, we've been able to explore a lot more of the kind of phase diagram of the dynamics. So to do that, we had to build a new version of the KRB experiment. The overall molecule production process in the second generation KRB experiment is the same. We laser and evaporatively cool a mixture of bosonic rubidium-87, fermionic potassium-40 to BEC in a degenerate Fermi gas. We use a Feshbach resonance to associate the atoms into weakly bound molecules, and we use Dirac to transfer them to the rotovibrational ground states. But in the second generation machine, we've made improvements to the atom number, the atom cooling process, which let us realize the first degenerate Fermi gas of molecules. In addition, we have in-vacuum electrodes that are shown in this picture that let us apply very high electric fields to the molecules. And we've been able to use those electric fields to control the collisions and enable efficient evaporative cooling, as well as to apply electric field gradients, enabling local control of layers in an optical lattice. Here I'll talk about how we use these electric fields to control the spin model of the molecules. We also have had to work very, very hard to control the single particle effects that would make the spin models unobservable. So the geometry of the electrodes is designed to give a very flat electric field across the sample to minimize gradients. We control the voltage of the electrodes carefully to minimize noise that would cause, for example, time-dependent gradients and dephasing. We also were worried about differential AC Stark shifts between the different states that would lead to dephasing from noise of your optical trap power. So when possible, we've been using a magic angle between the quantization axis and the polarization of the light, where the two states that we're using as our qubit have the same polarizability. Then finally, even after these techniques, there's still going to be some noise left over. So we use dynamical decoupling sequences that essentially consist of repeated spin echoes to cancel whatever remaining static and time-dependent noise we can. And using those, we can get a couple orders of magnitude enhancement of the molecule-molecule coherence time in our system. So how do we actually measure the XXZ dynamics in this platform? We use Ramsey interferometry, where we prepare a product state on the equator of the Bloch sphere. We evolve under our XXZ Hamiltonian for some time, and then we measure the decay of the Ramsey contrast, the length, which corresponds to a decay of the magnetization in the corresponding spin system. So, to provide some intuition on why you would expect contrast decay in this XXZ model, we can talk about the two-particle case, which Gabriel actually introduced in his talk this morning. Here we have oscillations between the product state and an entangled state, which is shown here, with a rate that is proportional to this chi anisotropy in the spin model. And because this one, the product state has a length of the Bloch vector of 1, but the entangled state has a length of the Bloch vector of 0, we see oscillations in contrast from the dynamics. So in 2013, at zero electric field, they were able to implement that system in the experiment, and they see these contrast oscillations, which was pretty exciting. And then also, in addition to the contrast oscillations, they see an overall decay of the contrast over time, which got faster as they increased the density of the sample. That comes from longer range interactions in your disordered environment. So now that we have this excellent control of the electric field, we recently decided to revisit those dynamics, but tuning the electric field. The measurement procedure is we will prepare some initial density at some electric field, and we'll measure the decay rate of the Ramsey contrast. We'll then, to make sure we're not measuring single particle effects, repeat that measurement at a range of different densities and look at the dependence of the contrast decay rate on the density. And then we can repeat this for a bunch of different conditions to scan out the behavior of the spin model as a function of electric field. And when you do that, you get something that looks like this, where at very low electric field and high electric field, you have fast contrast decay, but at around 6.5 kilovolts per centimeter, this chi term is 0, and we implement an isotropic Heisenberg XXX model under which the decay is very slow and dominated by single particle effects. And these measurements agree quite well with a theoretical model using the MACE technique, where essentially you compute the interactions for nearby strongly interacting clusters of molecules, and you take an average over all of the clusters, which was developed by Anna Maria Ray's group to explain the results from the previous spin exchange experiments. It's also worth noting that between 2013 and now, people have come up with other ways to explore these XXZ dynamics using Floquet engineering, where they'll drive some pulse sequence to change the sort of interactions that the system experiences. And they've been able to implement this in Rydberg atoms, nitrogen vacancy centers, and also in Wasim Bakker's molecule experiment. So to kind of get some intuition for what is happening, you have some initial state on the equator of the Bloch sphere, and that, where the spins are fully polarized, is an eigenstate of the isotropic S dot S term of the Hamiltonian. And there's some energy gap between that state and one where a spin is flipped, reducing the Ramsey contrast. But under the anisotropic SZ term, the Hamiltonian generates time evolution. In the all-to-all case, you would get spin squeezing through one-axis twisting. In the disordered case, you would get entanglement under local under with entanglement of the local spins. So overall, the dynamics are a competition between this gap protection term and then your anisotropy, which drives interaction. So it gets stronger as you get further from the isotropic Heisenberg model. So molecules can move. So we also decided to look at the XXZ model in the context of itinerant molecules, where we turn off the 3D lattice and let the molecules move within pancakes of a one-dimensional lattice. In that case, we can describe a molecule's state by where it sits within the harmonic oscillator modes of one of the pancakes. So in the direction along the k-vector of the lattice light, the trap frequency is very high and all the molecules are in the lowest energy state, but they can occupy other states in the two loose directions of the trap. So we can think about an XXZ spin model where instead of the indices corresponding to lattice sites, they correspond to modes in the harmonic oscillator. And what's kind of interesting about those harmonic oscillator modes is that the particular interaction strength between any pair of modes depends fairly weakly on which particular modes they are, since the molecules are sort of smeared out over the trap. So that justifies making a collective approximation where we think about these capital S's, which are the sum of the spins of all these molecules, and then these coefficients, which are averaged over all of the motional modes. And in that collective model, we would expect a mean field shift where the energy of some product state depends on the tipping angle on the Bloch sphere, where that energy shift is proportional to this chi parameter in the XXZ model. So we can directly probe that with Ramsey spectroscopy, where we vary the initial tipping angle, and we see phase shifts between where we tip it to pi over 4 on the Bloch sphere versus 3 pi over 4. And if we systematically scan that out for different electric fields, we find something that agrees pretty well with theory, where we can implement an icing model, a spin exchange dominated model at low fields, an icing dominated model at high fields, and then you get a zero crossing with the isotropic model in between. But it turns out that it's actually very challenging to implement just the spin model in these fully itinerant molecules because they run into each other. And we see quite fast contrast decay that scales with the density of the molecules. So what we think is happening that causes that contrast decay is elastic collisions between the molecules, which randomize the phase and cause dephasing of the molecules. And we think that the collision rate scales with the transition dipole moment of the molecules, which sets the collision cross-section. When we tilt the electric field to make a weaker interaction, we see a correspondingly slower collision rate. So that rapid loss made us start thinking about how we could control the motion of the molecules so we can still explore these tunneling, this extended Fermi-Hubbard model, but without the kind of loss that you get from collisions. So we implemented a shallow horizontal lattice where we still can have tunneling of up to a couple hundred hertz, but the molecules remain within a single band of the lattice and don't experience these very fast collisions. We also can have on-site interactions between the molecules. They're fermions, so you can only have a spin-up and spin-down molecule on one site in the lowest band. And then the on-site interactions are some combination of dipole-dipole interactions, a contact interaction, and an on-site loss. So if you think about what happens when you have this tunneling and on-site interaction, you can get a super exchange process where the interactions, where the nearest neighbor isotropic interactions are modified by a 4 tunneling rate squared divided by on-site interaction term. And for the molecules, the on-site interaction turns out to be negative. So as you turn up the tunneling rate, you shift the effective interaction between nearest neighbor molecules, and you can actually get this the isotropic part of the interaction to cross zero. It's worth noting that the JZ term is also modified, since it goes into the isotropic part, but that this chi anisotropy stays the same. And so you can come up with an effective spin model where your nearest neighbor interactions have this modified J-perp term, which comes from the standard dipole-dipole interactions plus super exchange, in addition to the longer range interactions, which are the kind of normal XXZ model that I've been telling you about. And you get some pretty rich dynamics if you think about the XXZ model with this tunability of coefficients, where when JZ is large and negative compared to J-perp, the ground state of the Hamiltonian is an Ising antiferromagnet, and you see some sort of relatively fast contrast decay in simulations of the system, where JZ and J-perp are comparable. The ground state of the system is an ferromagnet in the XY plane, where the ground state would be something on the equator of the Bloch sphere, and if you have an initial product state, you see dynamics where the coherence is well preserved. And then finally, if you make JZ large compared to J-perp, the ground state is an Ising ferromagnet, and you also see very rapid contrast decay for an initial product state on the XY plane. So if you take what happens where you tune the coefficients of the XXZ model with electric field on the x-axis and the tunneling rate on the y-axis, you can implement a fairly rich exploration of the phases of this Hamiltonian. It's worth noting that we don't have a full dynamical model for what's going on, and this phase diagram is sort of a very crude approximation. But we've started exploring it in the experiment. So if you operate at the Heisenberg point, we see basically a very, very slow contrast decay rate that's independent of density. We think we're dominated by single particle effects in that regime. And we also looked at 4.5 kilovolts per centimeter, which is slightly towards the spin exchange side, but still close to the Heisenberg point. And we saw the same thing. But when we went to lower electric fields, the dynamics started getting more exciting. We would see, as we increase the tunneling rate, a peak where the interaction-dependent contrast decay rate increased. And what we think is happening there is we're crossing from the regime in this blue region where it's an XY ferromagnet to this gray region where the ground state is an antiferromagnet and we see correspondingly faster decay. We also have, this is very recent preliminary data, we haven't even finished this curve, but we also explored this at a lower, even lower field, and we see similar dynamics, although more extreme since we're entering more into the antiferromagnet phase. And then finally, we've also done it in a high electric field where we expect, where we see fast loss when tunneling, or fast contrast decay when tunneling is turned off, because we're in this Ising ferromagnet regime. But then as we increase tunneling, we cross over into the XY ferromagnet regime where we expect slower contrast decay, and we see in the data that we reach single particle limited contrast when we have fast tunneling. So this is something that's very preliminary, and we're still continuing to explore the dynamics, try tuning the parameters, see if we can understand what's going on better. But it seems like we're already seeing something pretty exciting. So with that, I want to acknowledge my collaborators on the KRB experiment. Of course, June, postdocs, Henrik and June Yu, graduate student, Annie, and then Christoph, who visited us for the last 6 months from University of Innsbruck. He's at this conference as well as some alumni of the group, Junru, Kyle, and Will, who have contributed a lot of the kind of technical things that enabled these studies, and our theory collaborators, David Wellnitz, Thomas, who I think you'll be hearing from soon, and Anna Maria Ray. So yeah, with that, I'm happy to take questions.
Okay, awesome. So we have time for a few questions. Start. In like the last bit, you talk about dipolar interactions and on-site interactions, and you scan the electric field. So can you sort of, do you have any way to control them independently?
Yeah, so we can control the ratio of the dipolar long-range interactions and the on-site interactions, which are a combination of the dipole-dipole and the contact interactions, by changing the tunneling rate. We also we haven't tried doing this yet on the experiment. We also can control the ratio between the on-site dipolar interactions and the contact interactions by, for example, changing the depth of the vertical lattice, which would change the shape of the wave function, or maybe by tilting the electric field.
Can you go back to your last slide?
This one?
This one, yeah. So I'm reading this like going down the phase diagram as you turn up the tunneling strength. So for the blue one, for instance, you start off in XY, so you have this kind of no decay in your contrast, and then you cross your phase boundary and you get a peak. Mm-hmm. But now you're in the antiferromagnetic region. Why does the decay come back down here?
I think that we're not completely sure about that. I think when you get to very shallow lattices, the idea that you have a single band and super exchange breaks down. And if you turn off the lattice completely, you start getting back into this situation where you have elastic collisions. And I think that in that regime, it's a pretty hard system to model. So we're still thinking about exactly what's happening in the very shallow lattice limit.
And that kind of coincides with also the point where you're actually seeing a change.
Yeah. So I think that between, say, 2 and 10 recoils, the super exchange approximation works well, and we see significant changes within that region.
There are no further questions, so I suggest we thank Calder again.